consumption of petroleum products has doubled during the last 10 years and will undoubtedly double again during the next few years. If, as expected, consumption continues to increase at the present rate, then oil prospecting will move from the shallow waters of the continental shelf to deeper waters inaccessible to conventionally anchored drill ships and platforms. There is therefore an urgent need for a reliable and efficient drilling unit capable of working in economically acceptable conditions anywhere in the world on the continental shelf or beyond in deeper waters. Apart from its ability to move quickly from one location to another, the ideal drilling unit should be able to remain accurately in position over the hole in all weather conditions without being permanently anchored to the seabed. Being fully aware of future needs, La Compagnie Française des Pétroles, the parent company of the Total Group, examined the feasibility of building a dynamically positioned deep-water drill ship. With the help of Sommaser, ship owners, and Foramer, a French drilling company, the Total Group worked out a basic project. They called upon IHC Holland, a producer of specialized offshore drilling equipment, to take over the project and build the ship. An exhaustive research program, which included model tests in a towing tank, was begun, and it eventually brought the solution to a number of technical problems.
$90 voet toch?
Ja. 90 voet? Oh, in totaal ja. Ja, ja.
Dus 7
normaal wel.
meter en een beetje.
Normaal wel.
En
yes, I see what you mean, but if I may,
Elaborate wind tunnel tests were made to determine the behavior of the ship under winds at every angle of attack. By the action of wind, current and waves, the ship will be constantly moved away from the required position. By using variable pitch thrusters, it is possible to limit drift to less than 6% of the water depth. By intelligent adjustment of the pitch, the thrust exerted may be calculated to compensate for the effects of wind and current. So every time it drifts, the ship is returned to its working position over the hull. The action of the thrusters also makes it possible to modify the ship's heading, so as to minimize the influence of wind and current. Backward and forward drift in relation to the hull is compensated for by varying the pitch of the main propellers. Data from a series of tests conducted under different conditions was punched into a hybrid computer. The results provided by the computer showed that the project was feasible and that the ship was indeed capable of maintaining its position within a radius of 6% of the water depth in a steady 45-knot wind, with 60-second gusts of 65 knots. The results of these tests were checked and rechecked. The ship was now ready to be built. Two thrusters and two propellers are located aft, while 3 further thrusters are placed in the bows. The variable pitch thrusters are each driven by a 1500 horsepower electric motor, while the two main propellers are each driven by two motors with a total output of 3000 horsepower. The external diameter of the thruster blades is 8 feet, while that of the main propellers is 13 feet. Each of the forward thrusters is mounted on dampers to prevent noise from being transmitted to the crew's quarters situated almost directly above. The main switchboard is located aft. Immediately above it are the 5 diesel generators, each developing 3,400 horsepower at 1,200 RPM. The mechanical equipment of a modern drill ship is grouped conveniently around the moon pools, the mud pumps, the mixers, and the cement units. Above these, the hoppers and containers for the additives and pulverulent products, and a well-equipped mud laboratory. Directly alongside the moon pool are the large barite and cement silos. All these storage facilities and fuel reserves have been designed to enable the ship to stay in position for up to 3 months without any supply vessel. After the lower working platform is the Doris Comex deep diving installation, which can be used for saturation diving with 6 men to a depth of 1,000 feet. The blowout preventers fitted with modern equipment are handled on an area adjacent to the moon pool. This area is equipped with 2 hydraulic carriages, each capable of shifting BOPs of up to 70 tons and 28 feet in height between the storage room, the maintenance area, and the working area. The main hold and the 2 tween decks are set aside for the storage and mechanical handling of the drill and casing pipes. The 500-foot-long hull incorporates not only tanks holding up to 7,700 tons of fuel, but also drill pipes, casings, mud products, and all kinds of equipment and supplies needed for an offshore drilling operation. Only 8 months after keel laying, this hull was ready for launching.
Je te nomme Pelican et je te souhaite à toi et à tout ton équipage un avenir très heureux.
The forward part of the ship is devoted to crew's quarters. Particular care was given to the fitting out of these quarters since they were to be home for a 90-man crew. Navigational equipment is located on the bridge. Modern shipbuilding techniques were used so that the accommodation and navigation block could be installed in a single operation. An automatic horizontal racking system handles and stores 192 stands of 91-foot drill pipe. Through the combined action of gantry cranes, lifting devices and backup beams, each drilling string is placed in a vertical position inside the derrick. The full cycle takes about 65 seconds to complete. The ship is now ready to sail to its first location. The geologists and geophysicists have determined the exact drilling position. The first operation was successfully completed in the North Sea, where the widely differing weather conditions encountered by the ship proved the accuracy of all the theoretical calculations and tests that had gone before. Since the Pelican was mainly designed for waters too deep for conventional anchorage, the dynamic positioning system was specially developed to allow the ship to keep its position over the hull accurately without anchoring. Behind the man watching the screen is the brain of the whole dynamic positioning system. The data supplied by a taut wire inclinometer is converted into a position signal, which appears on the screen as a cross. The moving dot shows the ship's drift away from its position over the hull. Signals emitted from the ship's bottom trigger off responders located near the wellhead, which send signals back to hydrophones under the hull. These signals are converted into position data by sophisticated electronic equipment. Computers calculate the drift away from the required position and convert this data into orders to correct the pitch of the thrusters and propellers. This process is repeated continuously at short intervals during drilling. The ship is thus maintained accurately over the well, and the drilling operations can begin. No guidelines are employed when lowering the blowout preventer, so underwater television cameras and a diving bell are used when connecting the BOP to the wellhead. Is lowered by means of riser pipes, which provide a link between the seabed and the ship. Meanwhile, the mud is mixed. The handling of its ingredients is highly mechanized. The quality of the mud is constantly checked. The connection has been made. The divers are brought back on board, where they undergo decompression, an operation demanding the utmost care in mixing the gases.
Plongeur de surface, on a assuré. Ok. Est-ce que votre pâte est couverte? Bon, passez dans le sas alors. Ok.
Meanwhile, work continues on the drilling floor. The off-duty team are resting. The quality of the food is a very important factor for the well-being of the people working on the ship. Which is specially designed for drill ships, is lowered on the BOP. This piece of equipment allows the ship to be disconnected from the well almost instantaneously in an emergency. For efficient drilling, it is vital to maintain constant tension on the riser pipe which links the wellhead and the vessel to prevent buckling or moving out of the vertical. This is achieved by means of riser tensioners developed by IHC, which keep tension constant by taking up and paying out the lines as the ship rises and falls on the swell. On board the Pelican, a compensator has been introduced between the derrick and the crown block. This consists of a pair of hydraulic rams which convert the hook load into hydraulic pressure. The pistons of these cylinders are connected to the crown block by a fixed vertical frame. A Unicode converter maintains the hydraulic pressure at an almost constant level. During operation, the force exerted by the hydraulic rams serves to adjust the weight on the drill string. As the bit bites deeper and deeper into the ocean floor, Sophisticated machines silently watch and monitor the intricate equipment which keeps the ship precisely over the wellhead. A delicate interplay of man and machine produces maximum results with a minimum of human intervention. Today, the problem of energy sources is one of extreme urgency, demanding new solutions. The drillship Pelican is one of them. Capable of prospecting as yet unexplored territories at ever greater depths, and of discovering new oil and gas fields, it is helping to safeguard the world's energy requirements of the future. Pelican is designed, built, and operated by Total, Somerset, Foramer, and IHC.